In Part 3 of the General Performance Principles Climb lesson, you learnt about the rate of climb, the best rate of climb speed, and lastly, about some of the factors that affect the rate of climb, namely aircraft mass and configuration. In Part 4, you will continue the study of what factors affect the rate of climb, starting with the effect of air density.
Density is another important factor that affects the rate of climb. However, density also affects a lot of the variables in the formula for the rate of climb. Shown here is an expanded rate of climb formula, reminding you that power available is thrust multiplied by true airspeed, and that power required is drag multiplied by true airspeed. Let's just focus on the power available for the moment. Decreased density will decrease the thrust, but it will also increase the true airspeed. The overall effect is that the thrust loss is more than the true airspeed gain, meaning overall that the power available decreases. Looking at power required, decreased density will increase the true airspeed, but will have no effect on the drag. Therefore, the power required will increase. Returning to the graph, this means that the power available curves move down and to the right, and the power required curves move up and to the right. You'll notice that there is less excess power available, and this causes a reduction in the rate of climb for both aeroplane types. This effect will be repeated any time the density falls, which can be caused either by increasing altitude, increasing temperature, or by increasing humidity. We stated previously that the true airspeed for Vy increases with decreasing density. As pilots, we fly using indicated airspeeds, and therefore it's important to understand what happens to the indicated airspeed of Vy. In order that we may understand, a further explanation is needed. Shown on screen is a graphical representation of the relationship between indicated airspeed and true airspeed with altitude. We've already stated several times that with decreasing density or increasing altitude, the true airspeed must increase in order to maintain the same indicated airspeed. This graph shows the true airspeed increasing for a constant indicated airspeed. However, returning to Vy, we stated that the true airspeed for Vy increases slightly with altitude, as density decreases. You'll notice that if the true airspeed increases slightly with altitude, the indicated airspeed will decrease. In fact, Vy will eventually reduce to become the same value as Vx. This means that Vy, expressed as indicated airspeed, is actually decreasing as altitude increases. So, in summary, reduced density decreases the indicated airspeed of Vy and decreases the rate of climb. The higher the aeroplane flies, the more the excess power available diminishes, and therefore the maximum achievable rate of climb will decrease. An altitude will be reached where the excess power available decreases to zero, as shown. Therefore, the rate of climb will also decrease to zero. This altitude is known as the absolute ceiling. The graph on screen shows the excess of power for a typical aeroplane at mean sea level. Notice Vy is the speed that gives the maximum excess power available and maximum achievable rate of climb. As altitude increases, notice that the excess power available decreases, achievable rate of climb decreases, and the indicated airspeed for Vy decreases. At its absolute ceiling, the performance of an aeroplane is so reduced that it is unable to maneuver. Therefore, absolute ceiling is a rather abstract concept for a pilot. It's more useful for a pilot to know his aeroplane's service ceiling. Service ceiling is defined by the aeroplane manufacturers and aviation authorities as the maximum altitude where the best rate of climb airspeed will still produce a positive rate of climb at a specific number of feet per minute. The recommendation is to not exceed this altitude, because above it the performance envelope of the aeroplane is very small. If the aeroplane were to climb higher, the rate of climb would fall to 0. The aeroplane will not be able to climb any higher, and the absolute ceiling would be reached. At this altitude, Vy and Vx are the same speed. To find the absolute and service ceilings of your aeroplane, consult your flight manual and operate the aeroplane below the service ceiling to help maintain sufficient performance levels. To demonstrate the effect of wind, let's return to the original concept of the rate of climb. You'll recall that it was stated that the rate of climb is a function of the gradient and the forward speed. The formula on screen demonstrates this. In the case of a headwind, the gradient increases as shown, but the forward speed is decreased. Looking at the formula, one variable has gone up, the other variable has gone down. The net result on the rate of climb is that it remains unchanged. In the case of a tailwind, the gradient decreases, but the horizontal speed increases. Again, the situation is the same. One variable decreases, but the other variable increases. The net effect is that the rate of climb remains unchanged. Looking at both the headwind and tailwind examples together shows you that both aeroplanes are gaining the same height in the same time. Therefore, we may state that winds do not affect the rate of climb of an aeroplane. The last part of this lesson will deal briefly with some of the formulae you've seen so far, and how to rearrange them to suit various scenarios and questions. This first formula is the formula for the gradient of climb. The triangle on the right is a useful tool to help you rearrange the formula for any required situation. For example, if you are asked to calculate the weight, then the formula would be the thrust minus the drag over the gradient. Or, if you needed to calculate the thrust minus the drag, in other words the excess thrust, then take the gradient and multiply it by the weight. The second formula relates mainly to obstacle clearance type questions. Earlier on you were shown a typical obstacle clearance problem, and the formula used was the one shown on screen. Again, by using the triangle it's possible to rearrange the formula. If you were required to calculate the horizontal distance, you would use the vertical distance divided by the gradient. However, you may more commonly be asked to calculate the vertical distance. The vertical distance is found by taking the gradient and multiplying it by the horizontal distance. The last formula is very similar to the previous one. Instead of vertical distance, we have vertical speed, which is the rate of climb. Instead of horizontal distance, we have horizontal speed, which is the true airspeed. If you were required to calculate the gradient, then you would use the rate of climb divided by the true airspeed. Or if you were required to calculate the true airspeed, you would take the rate of climb and divide it by the gradient. Lastly, to calculate the rate of climb, take the gradient and multiply it by the true airspeed. Using these simple triangles to help you rearrange the formula can simplify the mathematical component of the JAA performance exam, and allow you to concentrate on the more theoretical performance aspects. This completes the lesson on climb performance. Ensure that you familiarize yourself with how various factors and environmental conditions affect your climb performance in terms of both the angle and rate of climb.